Let's work a few examples using the node voltage analysis. I'm going to describe a general method that you can use to basically analyze any circuit that you might be presented with. I'm going to describe the general method via an example, and you might recognize this example. We looked at it in the previous video involving the Kirchhoff voltage law. Here's a general method that we can apply to any circuit where we want to use the node voltage analysis method. First, we need to assign a ground. A ground is nothing more than a label. So we need to pick a point on our circuit where we can say this is 0 volts. Now, mathematically, we can pick any point in the circuit we want, but it makes sense to pick a convenient point. And normally, that point will make the most sense near a voltage source. In this circuit, we could, for example, pick our ground here at the base of the 12-volt source, or we could have picked it over here at the base of the 10-volt source. We now need to label all of our nodes. Now, some of the nodes are very easy to identify. For example, this node is clearly 12 volts higher than ground. There's no need to assign a variable to that particular node. I can just write 12 volts straight away. Some of the other nodes, though, we might not be able to immediately identify the voltages. For example, this node, which connects to this resistor, to the 10-volt source, and to this resistor, doesn't have a clear voltage. Let's label that voltage V sub A. The node down here, which connects to two 10-ohm resistors and the base of the 10-volt source, also doesn't have a very clear voltage. Let's label that V sub B. All of our nodes are now labeled. We're finished with step 2. Let's go on to the third step. The third step is to apply KCL at each node. This should give us a full set of equations and enable us to find all of the voltages in the circuit. We only have 2 unknown nodes. These are the 2 at which we need to apply KCL. Let's start with V sub A. Current in equals current out. This is our current in, V over R. Current out through that 10-ohm resistor is VA minus VB divided by 10, V over R. Now we have one more current. We could draw the arrow in either direction. I'm going to draw it towards the right. Let's label this current I. Since that current passes through a source, I can't use Ohm's law to express it directly. Let's now move on to node V sub B. Current in via the 10-ohm resistor is given by VA minus VB divided by 10. We have current coming in I through the 10-volt source, and we have current going out through that final 10-ohm resistor. We have 2 equations and 3 unknowns, but we also know that because we have a 10-volt source, we have a well-defined relationship between VA and VB. In fact, when I first labeled my nodes, I didn't necessarily need to call this one VA. I could have immediately written VB plus 10 because of that 10-volt source there. We now have 3 equations and 3 unknowns. Rather than go through the algebraic steps of solving these particular equations, I'm just going to write out the solution. I would encourage you to check it. VA is 11 volts, VB is 1 volt, and the current, as I have it labeled, is negative 0.9 amperes. In the problem, we were tasked with finding the voltage V. I can see that V is 12 minus VA. This means that the voltage V is just 1 volt. Let's look at a slightly more complicated example now and apply the same 3 rules for node voltage analysis. In this example, we're tasked with finding 3 different currents, I1, I2, and I3. Our first step is to assign a ground. I'm going to assign my ground here at the base of all 3 of the voltage sources. It's the most obvious place. Let's now label all of our nodes. Because I put my ground in a convenient place, some of my nodes are already obvious. We'll call this node 5 volts, we'll call this node 15 volts, and we'll call this node 10 volts because they're each their respective voltage above the ground. We have only one node to label with a variable for this circuit. Let's call that node VA. Going on to the third step, we just need to apply KCL at each node. We have only one node, and we have 3 currents entering that node. Those currents should add up to 0. Although I could write simply I1 plus I2 plus I3 equals 0, I can also apply Ohm's law as I go in my head. For I1, I can see that it's 5 minus VA over 10 ohms. I applied Ohm's law. For I2, I know that it's 15 minus V sub A over 10. And likewise, for I3, I know that it's 10 minus V sub A over 10, and the sum is 0. This equation is fairly easy to solve because the 10s just cancel out. I've determined that node VA is at 10 volts. I can now easily calculate the three currents. This is I1, this is I2, and this is I3. I already know what VA is, so I can immediately write down the solutions. I1 is negative 0.5 amperes. I2 is 0.5 amperes, and I3 is 0 amperes. Let's work one more problem using the node voltage analysis method, but without looking at the instructions this time. The first step is to label our ground. I'm going to put mine down here at the bottom because it's next to the negative side of the 10-volt source. We now need to label all of our nodes. We have one obvious node. This one is at 10 volts. Let's label our other two nodes, V1 and V2. We now need to apply the Kirchhoff current law at each node. Let's go ahead and label our currents as well. Although we might not need these currents in our equations, it's good to at least draw the arrows so we don't get the polarity confused. Let's start with node V1. Current in equals current out. I'm going to apply Ohm's law in my head as I go. Current in, we have I1 plus I5 equals I3. Let's apply KCL at node V2. We have I2 coming in, we have I4 and I5 going out. If it's confusing to you as to which V to write first in these equations, consider, for example, I5. We always start at the tail of the arrow and then subtract the voltage at the head. Therefore, I have V2 minus V1 when I write that equation. If you remember tail minus head, then you won't get confused. So we now have two equations and two unknowns. Let's go ahead and just solve it because it doesn't look too complicated. Starting with V1, I'm going to multiply everything times 100. For V2, I'm again going to multiply everything times 100. Let's try to simplify these equations by combining terms. Let's multiply the first equation by 3 and swap the two terms with V in it. If I add these equations, I can find an expression for V1. We should be able to now find V2 from the top equation. V2 is 5.45 volts. If we want to find our current I in the original circuit, we can apply the Kirchhoff current law at the 10-volt node. We can immediately notice that the current I is just I1 plus I2. I1 is given by this term, and I2 is given by this term. Knowing V1 and V2, we can determine that I is 118.2 milliamps. You might notice that this problem is superficially similar to one of the problems that I brought up before when I talked about resistors in series and in parallel. At the time I worked that problem, I mentioned that a more powerful solution method would allow one to combine resistors when they don't obviously look like they're in series or parallel. This is it. If we look back at the original problem, and if I were to ask, what effective resistor could I replace all of these resistors with in this problem, the answer is 10 divided by I. That will give me the effective resistance in this problem. In this particular problem, using the node voltage analysis method is one way to combine these resistors since they aren't obviously in series or in parallel. We can't apply the same trick that I applied earlier because in this particular problem, current is actually flowing through the 100 ohm resistor here in the middle. Let's look back at the problem that I considered before and re-examine it. In a previous video, we were tasked with combining these resistors. Since we might not know in advance that there's no current flowing through the 8 ohm resistor, let's rework this problem using node voltage analysis in order to find the equivalent resistance. We don't have a voltage source in this problem, so we're going to have to use a test source. Our strategy will be to attach a test voltage source, V sub t, to this circuit. That voltage source will carry a current I. If we want to know what the equivalent resistance is of this mess of resistors that we've attached, we just need to find the ratio of Vt to I. That will give us the equivalent resistance. Let's go ahead and try it with this problem. We already know that the solution should be 4 ohms because we calculated it in an earlier problem. Hopefully we'll be able to get it with this more powerful method now. Using the node voltage analysis method, I'm going to put my ground here. This voltage at the top is labeled Vt. Let's call the node over here V sub A and the node here V sub B. We now need to apply the Kirchhoff current law at each of our nodes. Let's go ahead and label our currents, even though we might not use the letters in our equations. Let's start with node V sub A. We have I1 and I5 in, and we have I3 coming out. At node V sub B, we have I2 coming in, and we have I5 and I4 going out. At node V sub T, we have I coming in, and we have I1 and I2 both going out. You might notice that we have 3 equations, but we have 4 unknowns. How are we going to be able to solve it? Well, it turns out that we don't need to find every single variable. We only need the ratio of V sub T to I. We have enough information to solve the circuit. Let's go ahead and do it. I'm going to multiply every term by 8. I'm going to multiply every term again by 8. I'm going to go ahead and substitute for I with our equation for the equivalent resistance. I'm just going to call it R now. I is Vt divided by R. Let's multiply every term times 4R. We now have 3 equations and 3 unknowns. Let's group terms together now. With this set of 3 equations, we can eliminate the variables VA, VB, and Vt, and we would be left with an expression for R in terms of just the numbers. Rather than show all of the steps of the algebraic simplification, I'm just going to show the solution. The resistance R, or the equivalent resistance, winds up being 4 ohms, just as we expect. You might notice that VA, which is 2/3 of the test voltage, is the same as V sub B, which is also 2/3 of the test voltage. The fact that these 2 voltages are the same illustrates very clearly that the current flowing through this 8 ohm resistor in the middle ought to be 0. That's exactly what we inferred earlier when we performed the trick. But had we chosen other resistors, for example, if this had been 5 instead of 4, then I sub 5 would not have been 0, but this node voltage analysis method would have still allowed us to come up with an answer for the equivalent resistance. If you enjoyed watching this video, then you might be interested in following our playlist and learning more about the fundamentals of electrical circuits.